Pick up a rock. Any rock. A nice gray one from the side of the road. Hold it in your hand. Feel the weight of it. Dull, cold, about as boring as anything you could imagine. And if I were to tell you that inside that rock there is a fire more violent than anything on the surface of the sun, you would think I was out of my mind. But I am not out of my mind. The fire is there. It is inside that rock, inside every glass of water, every blade of grass, every bone in your body. Every atom of everything you have ever touched in your entire life is carrying this fire. And the disturbing part is not that it is there. The disturbing part is what you have to do to let it out. You have to break something absurdly small. And when you do, when you crack open the heart of an atom, you discover something about the universe that frankly I wish were not true. I'm Richard Feynman. I've spent my life trying to figure out how the world works, not by looking at the labels we put on things, but by looking at the things themselves. Today I want to talk to you about the underlying machinery of what's happening here, why it's so fascinating, and how we can understand it by breaking it down into its simplest, most fundamental parts. If this kind of exploration excites you, subscribe to this channel right now, hit that like button, and share this with someone who deserves to have their mind rearranged. Drop your location in the comments. I genuinely want to know where in the world curious people are watching. Now let's go find out what's really happening inside that rock. Let me start with the atom. You've heard the word? Everybody has heard the word atom. The building block of matter, the little indivisible bit of stuff that everything is made of. And the first thing I want to tell you is that the word is wrong. Atom comes from the Greek word atomos, meaning uncuttable, indivisible. The whole point of what I am about to tell you is that atoms can in fact be cut. They can be split. And when you split them, you find something nobody expected. But first, how small is an atom? Take an apple and blow it up until it is the size of the earth. At that magnification, the atoms in the apple would be roughly the size of the original apple. That is how small we are talking. If you lined atoms up side by side, it would take about 10 million of them to span the width of a single human hair. For most of history, nobody knew atoms existed. It was not until the early 1900s that atoms went from probably real to definitely real. Einstein helped settle the matter in 1905, the same year. He published the equation that will haunt the rest of this talk by showing that the jittery motion of pollen grains suspended in water could be explained perfectly if water was made of vast numbers of tiny particles bumping into the pollen from all directions. The atoms were real. And once we knew that, a whole generation of physicists started asking the dangerous question, what are atoms made of? An atom, it turns out, is mostly empty space. I mean, really staggeringly, absurdly empty. Imagine the atom were the size of a football stadium, the whole stadium, seats and parking lot and all. The nucleus would be a marble sitting on the 50-yard line. The electrons would be like gnats flying around somewhere up in the nosebleed seats. Between the marble and the gnats, there is nothing. Empty space, void. That is what you are made of. That is what the rock in your hand is made of. The nucleus is where almost all the mass lives. It is made of two types of particles, protons, which carry a positive electric charge, and neutrons, which carry no charge at all. They are crammed together, packed side by side in this absurdly tiny space. The density of nuclear material is almost beyond comprehension. A teaspoon of pure nuclear matter would weigh about 10 billion tons, more than the weight of every ship and every navy on the planet, packed into a space that would fit on the tip of your finger. Right away, there is a serious problem. The protons are all positively charged, every single one. And what do positive charges do when you put them near each other? They repel. They push apart violently. Every single instant, the protons in every nucleus in your body are screaming at each other, "Get away from me!" So why hasn't the nucleus exploded? There must be another force, something stronger than electromagnetism at close range. And there is. We call it the strong nuclear force. At short distances, it is roughly 100 times more powerful than electromagnetism. It grabs neighboring protons and neutrons like a wrestler and pins them in place, But the strong force has a peculiar property. It only works at extremely short range. If two protons are sitting right next to each other, cheek to cheek, the strong force grabs them magnificently. But move them apart by even a few femtometers, just a few millionths of a billionth of a meter, and the strong force drops to essentially zero. It vanishes. The electromagnetic repulsion, meanwhile, decreases with distance much more gradually. It has a long arm. The strong force has a very, very short arm. Can you see where this is heading? In a small nucleus like helium, everything is fine. Everybody is close to everybody else. The strong force wins easily. But as you add more protons and neutrons, the nucleus gets physically larger. Protons on one side sit quite far from protons on the other side. The strong force between those distant protons, zero. But the electromagnetic repulsion between them is still there, still pushing, still trying to tear the nucleus in half. As the nucleus gets bigger, the electromagnetic side gains ground. The nucleus becomes less stable, more fragile, like a water droplet that has been stretched too far, quivering, ready to break. This competition between the strong force and electromagnetism is the single most important idea in nuclear physics. It is the reason stars shine and the reason bombs explode. Physicists plot something called the binding energy per nucleon, how tightly each proton or neutron is held in the nucleus. If you graph this for every element from hydrogen to uranium, you get a curve that rises steeply for light elements, peaks around iron and nickel, and then gradually falls for the heavy elements. Think of this curve as a valley. Iron is at the valley floor, the most stable nucleus in nature. Elements on either side are climbing the slopes, and nature, as she always does, wants to roll downhill toward iron. For light elements, rolling downhill means fusing together. When hydrogen nuclei fuse into helium in the core of the sun, the helium is more tightly bound, more stable, closer to iron on the curve. Energy is released, that is why the sun shines. The light on your face is the sound of that downhill slide. For heavy elements, rolling downhill means splitting apart into smaller pieces closer to iron. When a uranium nucleus splits into barium and krypton, those products are more tightly bound than the uranium was. Energy is released, that is fission. Fusion rolls down one slope, fission rolls down the other. Both release energy. Iron is the cosmic drain, the destination, the dead end where nuclear energy goes to rest. Now let me split an atom for you. Take uranium-235, 92 protons, 143 neutrons, all jammed into a space a few femtometers across. It is a big, heavy, unhappy nucleus, quivering, barely holding together. A slow-moving neutron drifts in and is absorbed. The nucleus is now uranium-236, and that one extra neutron, the energy it brings, is enough to tip the balance. The nucleus begins to deform. It stretches into an oval. A waist forms in the middle, like a peanut shell. The strong force across that thin neck is losing its grip. The electromagnetic repulsion is winning. The neck gets thinner and thinner, and then snap. The nucleus ruptures in two. Two fragments go flying apart at roughly 3% of the speed of light. Typically, you get something like barium-141 and krypton-92. Along with the two fragments, 2 or 3 free neutrons shoot out, and gamma rays, high-energy photons, invisible but ferocious. But the violence does not end there. Those fragment nuclei are not stable. They have too many neutrons. So over the following minutes, hours, days, and weeks, they undergo a cascade of radioactive decays, emitting beta particles, emitting gamma rays, shedding excess energy, each decay converting a tiny bit more mass into energy. This is what makes nuclear waste so dangerous, the long, slow afterburn that keeps going for thousands of years. And here is the part that disturbs me most. If you carefully weigh everything before the fission event and then carefully weigh everything after the two fragment nuclei, the free neutrons, the gamma rays, the total mass afterward is less. Not by a lot, by about 1/5 of the mass of a proton, a sliver of a fraction of a percent. But it is real, measured, confirmed, undeniable. Mass has disappeared, matter has vanished. It did not hide, it converted into the kinetic energy of the fragments, into gamma rays, into heat and radiation and blast. Mass turned into energy, stuff turned into motion and light. This is E equals sine mc quadrat. Energy equals mass times the speed of light squared. The speed of light is 186,000 miles per second. Square that and you get the exchange rate. How much energy is hiding inside a little bit of mass? The number is enormous, which means even the tiniest disappearance of mass produces a tremendous release of energy. A single pound of uranium-235 fully fissioned releases the same energy as burning roughly 3 million pounds of coal. 1 pound versus 3 million. The energy was locked inside the mass all along, waiting patiently for billions of years since the supernova that created the uranium. Every chemical reaction you have ever witnessed, every fire, every explosion, every combustion engine converts about 1 part in a billion of mass into energy. Nuclear fission converts about 1 part in 1,000. That is 1,000,000 times more efficient. And even fission only unlocks a tiny fraction of the total mass energy locked inside matter. A single raisin, 1 gram, holds about 25 million kilowatt hours of total mass energy, enough to power an average home for over 2,000 years. Fission unlocks about 0.1% of that. And even that 0.1% is enough to power cities or destroy them. Now let me take you 1 layer deeper, the deepest layer, and to my mind the most unsettling. Protons and neutrons are not fundamental particles. They have guts. Each proton is made of 3 smaller particles called quarks, bound together by exchange particles called gluons. And the strong force at this level does something no other force in our everyday experience does. When you try to pull 2 quarks apart, the force gets stronger. Pull harder and it pulls back harder. Pour enough energy into the gap between them and the energy materializes. It converts into new quarks, new particles of matter created from pure energy popping into existence right there. You tried to isolate a quark and instead created new pairs. The universe refuses to let you see a quark alone. It will manufacture matter from energy before it allows that to happen. This is called confinement. It tells you something breathtaking about the nature of reality. There is no hard line between mass and energy. They are not 2 separate substances. They are 2 faces of the same thing. Energy becomes mass. Mass becomes energy. The boundary is not a wall. It is a revolving door, and things pass through it in both directions, constantly, everywhere, all the time. When you split a uranium nucleus, you are playing at the edge of that revolving door. Some of what was previously counted as mass, as the solidity of the world, exits through the door and appears on the other side as kinetic energy, as gamma rays, as light and motion and destructive power. This, I believe, is what is truly disturbing about splitting an atom. Not the explosion, though the explosion is terrible enough. What is disturbing is the philosophical shock, the revelation that matter, the thing your life is built on, the thing you are made of, is not fundamental. It is a temporary arrangement, a knot tied in energy. And knots can be untied. Everything you experience as solid and permanent is actually a balance, a tension, a negotiation between forces. The strong force holds the nuclei together. Electromagnetism pushes them apart. The balance holds for billions of years, but it is always a balance, always a truce, and truces, given the right conditions, can break. The universe does not pretend to be something it is not. We are the ones who impose the idea of permanence onto it. We looked at rocks and mountains and said, this is solid, this will last. But the rocks are made of atoms, and the atoms are made of nuclei, and the nuclei are battlefields. They have always been battlefields. The permanence was our invention. The fire is the reality. People sometimes ask me whether physics makes the world seem less wonderful. Because when you explain a sunset in terms of photons scattering through the atmosphere, have you not taken the beauty away? And I always say no. No, you have not, because the truth is more astonishing than the myth. The rock in your hand is a relic, an artifact of stellar nucleosynthesis, carrying energy from a supernova that happened billions of years before the Earth formed, bound together by a force that operates at distances smaller than anything you will ever directly perceive. The rock is boring only if you do not know its story. If you know its story, the rock is one of the most extraordinary objects in the universe. This is what physics does. You start with a rock. You ask what it is made of. Atoms. What is inside the atom? A nucleus and a cloud of electrons. What holds the nucleus together? The strong force battling electromagnetism. What happens when that battle is lost? Fission. Mass disappears and energy pours out. Where did the energy come from? It was the mass. The mass was the energy all along. What is mass? Frozen energy. Locked energy. Energy pretending to be solid. You picked up a rock, the most ordinary object in the world. And by the time you followed the questions all the way down, you arrived at a revolution in our understanding of what reality is made of. The atom splits, mass disappears, and energy floods into the world like water through a broken dam. For one brief, violent, clarifying instant, the universe shows you what is really going on beneath the surface. So let me leave you with this. Whenever you next pick up an object, a coffee cup, a pencil, a child's hand, hold it for a moment. Feel its weight, its warmth, its realness. Know that what you are feeling is not simply stuff. What you are feeling is energy, a staggering, almost incomprehensible amount of energy bound so tightly by the forces of nature that it behaves like a solid, permanent, trustworthy thing. But beneath that calm exterior, there is a fire that has been burning since the first atoms were assembled in the furnaces of dying stars. A fire older than the earth, older than the sun. A fire that will outlast everything you know. You are holding it right now. You are made of it right now. Frozen fire pretending to be a person. Does the world feel different in your hands?